Welcome to page 2 of the three-dimensional coordinate system, and what we're going to focus on right now are what surfaces look like. So we have equations, and we're going to be able to create a surface in the three-dimensional coordinate system just based off of the variables that are given, just based off the equation. And so I'm going to show you what the following equations are going to give us in the three-dimensional coordinate system. So we're going to start off with the z equals 2. So I'm going to draw a three-dimensional coordinate system. We have x, y, and z. And for a, we're just told that z equals 2. So all I need to do is go up on the z-axis at 2, and I'm going to create I'm just going to put a dot there. And because the only thing that's defined is z, and it tells me that z has to equal 2, everywhere on this graph, z has to be 2. So what we're going to create is we're going to create a horizontal plane at z equals 2. And it's going to be a horizontal plane. It's going to be 2 units above the xy plane. And if you're going to use words, that's how you would describe it. So I'm just going to go ahead and create my plane. And I have a highlighter here just to show you that, hey, that's a plane. And this plane, is going to go off in every direction. It goes on for infinity in all of those directions. And that's how you sketch z equals 2 on a three-dimensional coordinate system. So when I ask you to describe, you can describe this, a few ways. And so what I'm going to do is I'm going to go ahead and read this. But in the three-dimensional coordinate system, the equation z equals 2 represents the set of x, y, and z. Because we're dealing with a three-dimensional coordinate system, we use x, y, and z, where x is all real numbers, y is all real numbers, and z equals 2. So in this class, I don't know if you've seen this before, but there's that little symbol that just means that, x is in the set of all real numbers. All right. And z equals 2. So the set of all points whose z coordinate is 2. All I would ask you to write to explain this is to say that this is the horizontal plane that is parallel to the xy plane and is 2 units above it. All right, that's all you would have to use as a description for this plane. All right, so the next one hopefully will be pretty easy for you, knowing that, okay, x equals 3. So again, I'm going to draw a three-dimensional coordinate system. X, y, and z. And for this equation, we know that x is always defined as 3. So I'm going to go out 3 units on the x-axis, and it's just going to be a plane at x equals 3 on the x-axis. And this plane, let's see if I can draw that a little bit better. And this plane is going to be parallel to the zy plane. And it's up on the x-axis. And so, to define that, again, we basically use the same type of language that we use over on the left. In the three-dimensional coordinate system, the equation x equals 3 represents a set of x, y, and z, where x is 3, y can be any real number, z can be any real number. The set of all points whose x coordinate is 3. So again, all I would ask for you to write is this is the vertical plane that is parallel to the YZ plane in 3 units in front of it. The last one is a little bit different. We have the equation x plus y equals 3. So now we're defining 2 variables. The 2 variables that we will be defining are going to be x and y. And you can look at this as x plus y equals 3, or we can turn this into something we're more familiar with. We have an equation in 2 variables, and so we can solve for one of these variables. So we're going to say y is equal to 3 minus x. And so now we can put it into slope-intercept form, where our slope is -1, and our y-intercept is 3. So when we draw the three-dimensional coordinate system, what we're going to have cannot there we go, get through the origin. So what we're going to have is we're going to have a line that is defined by both x and y. And what it's telling us is that the sum of x and y is always 3. So we got to find that line where we add the x and y coordinates, and we're always going to get 3. So I want us to use the slope-intercept, and I'm just going to graph this how I would graph it on a two-dimensional plane. We're going to have our y-intercept at 3, and then we have a slope of -1, so we can go down 1 and to the right, or 1, or down 1 and come to us, towards us 1, down 1, come towards us 1, down 1, come towards us 1. And then here you have our line where the sum of x and y is always going to be 3. And again, it's going to go forever in both directions. But I'm just going to go ahead and just show the plane here. And there's our plane. It's going to be a diagonal plane now on x and y. And so again, we can write it out as, and again, I just put this into words so that you can also see it. The equation x plus y equals 3 represents the set of all points in the three-dimensional coordinate system whose x and y coordinates have a sum of 3. Or, equivalently, we can write it in slope-intercept form, y equals 3 minus x. This is the set x, 3 minus x. See, notice right here for the y value, oops, did not mean to do that. Notice for the y value, I went ahead and put 3 minus x because we defined y to be 3 minus x. And so I went ahead and put 3 minus x for y. And z, where x can be any number and z can be any number. I don't have to define y because I changed, how I defined y in terms of x's. So that's why you don't see, y can be any real number, which is a vertical plane that intersects the xy plane in the line y equals 3 minus x and z equals 0. So again, if I ask you to describe this, you would say a vertical plane that intersects the xy plane in the line y equals 3 minus x, z equals 0. Now, the last thing that we're going to talk about on this page is going to be the distance formula in 3 dimensions. If you notice, again, the distance formula for 2 dimensions is listed as basically this formula right here. X sub 2 minus x sub 1 squared plus y sub 2 minus y sub 1 squared. Well, now the distance formula, you can see we're just adding in that last coordinate. So now we're just adding in the z coordinate, and there's not going to be anything that's different. All right, so now let's use the distance formula to determine that we have 3 vectors, p, q, and r, and we determine if these vectors form a right triangle. Or actually, these aren't vectors, these are just points. And so we're going to see if when we connect these points, does it form a right triangle, and is it also an isosceles triangle? So the first one that we're going to find is going to be PQ. So one thing I encourage you to do is I'm going to be doing the work. If you feel like you don't need to see the work, go ahead and skip, ahead to just the answers, and you should be able to understand this. Again, this section right here is not going to be overly difficult. So I'm going to take my values for Q and P, and I'm going to go ahead and take my x's, 4 minus 2 squared, plus 1 minus -1 squared, plus 1 minus 0 squared. And I'm going to go ahead and do 4 minus 2 is 2 squared is going to be 4. 1 plus 1 is going to be 2. So 2 squared is also 4. And then we have 1 minus 0, so 1 squared. So we get plus 1. Add all those up, we're going to get the square root of 9, which is just 3. So PQ gives us 3. The distance from P to Q is 3. So now let's find the distance between P and R. So again, just use the distance formula. 4 minus 2 squared plus negative 5 minus negative 1 squared, and then plus 4 minus 0 squared. So 4 minus 2 gives us 2, so 2 squared is 4. Negative 5 plus 1 is negative 4. Negative 4 squared is going to be 16. And 4 minus 0 is just 4, so 4 squared again, and it gives us another 16. 16 plus 16 is 36. 36 plus 32. 32 plus 4 is 36. Square root of 36 gives us 6. And then the last one, Q and R. And we have the square root. And we're going to do 4 minus 4 squared plus negative 5 minus 1 squared plus 4 minus 1 squared. And we are going to get 0 squared is 0. Negative 6 squared is going to be 36, so plus 36. 4 minus 1 is 3, so 3 squared is 9. Add that, we get square root of 45. And the square root of 45 can be broken down to 9 times 5. Square root of 9 is 3, so 3 square roots of 5. Alright, and now what we want to determine is it a right triangle or is it an isosceles triangle? Well, we'll first look for an isosceles triangle just because that's easier to tell if it is. And is it an isosceles triangle? I hope you're able to answer that no, because two sides have to be of the same length and we have 3 different lengths. So no, it is not an isosceles triangle. And again, I'll highlight the answers in yellow. And now we want to determine if it's a right triangle. You probably understand how to figure out if it's a right triangle. Does it hold true to the Pythagorean theorem? So we need to determine, okay, what's the largest side? Is it 3, 6, 3 square roots of 5? Again, it's easier to go ahead and look at where it was just under the radical without having to simplify it if you're having trouble with that. And so we know that QR is going to be the hypotenuse. It's going to be the longest side. So when we're filling out our Pythagorean theorem, we're going to let QR be the hypotenuse. So we have 3 squared plus 6 squared equals, and I'm going to use this square root of 45 squared. I'm not going to square 3 square roots of 5. It's easier to deal with square root of 45. And so this gives us 9 plus 36 equals 45. And of course that checks out. So yes, it is a right triangle.